going to go through the notes for 342. I apologize in advance. This is going to be a long video. I've gone ahead and worked out the problems so you don't have to wait on me to write. I typically don't do that. I don't like to do that. I like to work them out with you. However, I just feel like if they're already worked out, I can go a little quicker, but you feel free to pause, copy, catch up, work out the problem, okay? You have the advantage of pausing the video, and if you don't understand something, you can rewind the video. So I'll do the best I can, but it's going to be a long one. The ones so far have been kind of short. Tomorrow's is going to be short, but sorry, you have to endure my voice for a long time today. All right, so just a reminder of average rate of change versus instantaneous rate of change. And remember, instantaneous rate of change is paired with the word derivative and slope of the tangent in your mind. So today we're going to look at kind of linear motion. So like straight up, straight down motion, or straight left, straight right motion. And we're going to look at if there was something moving up and down or left and right, where did it start? Where was it at a certain time? How fast was it going? What direction was it going in? Things like that. So the position function gets us the position. If we're looking at something like that's being shot up into the air, maybe we're looking at the height of the object. If we're looking at something that's moving left and right, how far left or right of the origin was it at a certain time? So that's going to be the position function, and for some reason, the name of the position function is S. Don't know. That's just the way it is. It's going to be the way it is the whole year. Position function is S. Displacement, this is a really important word. This is not the same as total distance. So it's very similar, but displacement and distance mean two different things. Displacement is going to be the change in the position, okay? Just the change in the position. So, like in slope, we would be looking at y2 minus y1 over x2 minus x1. This would be the change in my y values, or in this case, the change in my s values. Velocity, this is going to be the instantaneous rate of change of position. So the velocity is going to be the derivative of the position function. All right. Speed and velocity. Some of you interchange those words if you're not in physics. You think velocity is how fast you're driving on the road. That's speed. Velocity, when we're looking at up-down motion versus left-right motion, velocity means how fast was it going and what direction was it going in. So when it was traveling at this speed, was it traveling on its way up or on its way down? Or was it traveling toward the left or toward the right? Got that? Acceleration is how fast the velocity is changing. Now, think about this in a car. You can be traveling, let's say you've got your cruise control set at 65 miles an hour on 265. And you're just cruising along at 65 miles an hour, and then somebody's coming up on the on-ramp right beside you, and you need to get out of their way. You're either going to speed up, you're going to accelerate so that you go a little faster than 65 miles an hour, or you're going to decelerate so that you slow down and let them move in. So you're going to go less than 65 miles an hour. Of course, that's all if there's a car over there in the fast lane blocking you. Otherwise, just get out of their way. So acceleration is how the velocity changes, and acceleration is the derivative of velocity. So you can write it as v prime, or you can write it as the second derivative of position. And jerk is how the acceleration is changing. So think about this. When you accelerate too quickly in your car, what happens to your head? When you decelerate too quickly in a car, what happens to your head? It jerks. Huh, nice word for it. So we've got position, first derivative velocity, second derivative acceleration, third derivative is jerk. Now, let's look at a velocity graph. And let's see, I've written some things on it. I've looked at my window. It goes from -4 all the way to 36. So I labeled some tick marks for you. And it goes from -7.5 to +7.5. So I labeled those tick marks for you. So this is time. So this is 4 seconds, 8 seconds, 12 seconds, 16 seconds. And what's graphed is this girl's velocity. Girl, yeah. All right, so this looked like a fun experiment. Student walks around in front of a motion detector that records her velocity, and she stores the data in her graphing calculator. Don't we all do that? When is her speed a maximum? So I'll try not to forget to answer that question, but I just want to look at the graph for just a minute and kind of get you used to looking at a velocity graph. So for her, when I guess the video started to record her, so at time 0, her velocity was 0. So when it started to record her, she wasn't even moving. And then, like from 0 seconds to 4 seconds, her velocity was increasing and it was positive. So she's picking up speed, picking up speed, picking up speed. So from 0 to 4, she's starting to walk faster and faster and faster in the positive direction. How do I know that? Because these velocity values are positive. So she's like walking toward the right. So she's walking, speeding up, speeding up, speeding up toward the right. Here, her velocity stays the same. Her velocity is like 4. So she's walking at a constant pace. And it's positive, so she's still going right, same speed. Still going right, same speed. At 8 seconds, these velocity values are still positive. She's still going right, but she's slowing down. She's still moving to the right, she's slowing down. Oh, at about 14 seconds, she stopped. And then what did her velocity do? Then her velocity became negative. So now I think she was moving to the right, she sped up, constant, she slowed down, still right, still right, still right, stop. Turn around, go left. Now she's going left, speeding up, speeding up, speeding up, speeding up. Left, 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 faster, 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 faster. Left, 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 slower, 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 velocity is 0, stopped. And then you can see that her velocity was 0 from about 26 seconds to 32 seconds. Maybe she stopped and tied her shoe. I don't know. And then she started walking toward the right again. So I'm going to put an R right there because this whole time, from 0 to 14, she was headed toward the right. Here her velocity is 0. Here, her velocity is negative. She was headed toward the left. I'm going to put an L there for left. And up here, she was headed toward the right again. Okay. Now, back to the question. When was her speed a maximum? Well, I think that around, like from 4 to 8 seconds, her velocity was, positive 4. However, at about 20 seconds, her velocity was negative, maybe -7. Her velocity was -7. At which time was she moving the fastest? It would be this time. She's moving faster here, just toward the left, than she was moving here. So I think the answer to the question would be at about 20 seconds. All right, moving on. In case you're in case you're not given, like, I don't know if you're going to need these or not, but this is the free fall constants, or like the force of gravity. So in English units, gravity is 32 feet per second. But keep in mind that, yes, the pull downward is 32 feet per second. When we use that in an equation, we use a negative on it because it's a downward pull. And then in metric, it's 9.8 meters per second squared. Again, when we use that in equation, it's a negative because it's a downward pull. All right, we're not going to need those in today's notes. Today's notes, all the values are already given for you. So here we go. A dynamite blast propels a heavy rock. So the rock was sitting on the ground, it blew up, and it blew straight up, okay? So it straight up, its initial velocity, this is so important, its launch velocity, its initial velocity was 160 feet per second. Initial velocity means that's the velocity the moment the experiment began, so at time equals 0. When t equals 0, v is 160, positive 160, because it's going up. That's its velocity. It reaches a height up. Okay, so this is an equation. This is an S equation. It's the position function. And in this case, it's the height function. So it starts at 0. It's propelled straight up in the air. It's gonna rise and rise and rise and rise. Stop, fall and fall and fall and fall. Boom, until it hits the ground. Okay? Position function. Part A, how high does the rock go? So it's going to be propelled up in the air. The height is going to increase, increase, increase. The velocity is going to be positive, 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 positive. It's going to stop in midair for just a brief moment. So its velocity is going to be 0. And then it's going to start to fall again. How high does the rock go? So we could do this one of two ways. You could think back to algebra when you looked at this as an upside down parabola, and you could be like, oh, I'll use algebra on this problem. I just need to find the vertex. X equals the opposite of b over 2a. You could do that, but that's not going to help you later on in the problem. So let's use calculus. Let's find where the tangent line to my upside down parabola is horizontal. Or in other words, when velocity positive, 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 velocity 0, negative, 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 negative. How about let's find where my velocity is 0. So I used my position function and I took the derivative of it. This is my velocity. You can label it S prime, you can label it V, doesn't matter, whatever you want. So here's my velocity function for any time. I want to set my actual velocity, all of this, equal to 0. And then I solved it and I got 5 seconds. So, boom, the rock blows up, 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 up. At 5 seconds, it just hung there for a moment before it started to fall back down. Does that answer the question for part A? Oh, no. Part A doesn't say at what time did it reach its maximum height. What was its maximum height? How high did it go? Well, this is asking for the height, the position. When? 5 seconds. So knowing that at 5 seconds it had reached its maximum height before it came back down, I'm going to plug 5 into my position function. There we go. It went 400 feet in the air. Okay, part B. What was the velocity and speed when it's 256 feet above the ground, way up, way down? Okay, so for part B, when the height, okay, so this is important. Give me the velocity and speed. That means I'm going to need to use the derivative when the height is 256. So for part B, I'm going to have to use the velocity, which is the derivative. I've already got that. How about we take the position function and set the height to 256. Position function, I'm going to set my height to 256. Now I'm going to solve it. It's quadratic. Get everything on one side. I moved them over here because I wanted this to be positive. I divided everything by 16, and I factored it. Oh, wait, hold up. I got 2 times, 2 seconds and 8 seconds. I got 2 instances where my height was 256. Is that right? Are there 2 times that the height of the rock was 256? Absolutely. At time 0, the rock was on the ground, so its height was 0. At 2 seconds, it was on its way up, and it reached 256 feet, I think, and it kept going until 5 seconds, it reached 400 feet, and then it started coming back down, and at 8 seconds, it was at 256 feet again on its way back down. So, the velocity, it's asking for what, I know how high it was, how fast was it going right then, and how fast was it going right then. So the velocity at 2 seconds, I just plugged it in, was positive 96. Makes sense, it's on its way up, positive velocity. At 8 seconds was negative 96. That makes sense. At 8 seconds, it was on its way down, negative velocity. Part C asks us for acceleration at any time. Okay. Oh, sorry. Part B asks for speed also, and speed is the absolute value. So speed is going to be 96 both times. Velocity, positive on its way up, negative on its way down. All right. Part C, acceleration. Acceleration is the derivative of this, second derivative of that. I found it. This is weird if you're not a physics person. I think this is physics. I don't know that this occurs anywhere else. So keep in mind, acceleration is the rate of change of velocity. So it's going to be the change in velocity over the change in time. Think about how velocity is measured. The change in velocity, that means my numerator is going to be measured in feet per second. My denominator is going to be measured in seconds. So how is it changing? It's changing at, it's decreasing 32 feet per second every second. And another way we write that is feet per second squared. Acceleration, got it. When does the rock hit the ground? Okay, so for part D, when does the rock hit the ground? I want my height to be 0. I want my position to be 0. So, I did that. Part D, I set position equal to 0. That's what it looks like, equals 0. Factored it, solved it. There were 2 times when the height was 0, initially and after 10 seconds. Which one of these is when it hit the ground? This one. hopefully that's all good. And I know I used an extra page for mine. I could have squeezed it all on one page. I totally squeezed it all on one page in my notes. But it worked out better for me to just scroll here. All right, flipping to the last page. Now we're still doing, where am I? There we go. We're still doing linear motion. But this time, the linear motion is going to be left-right. So I think what I'm going to do, and I really wish that you could I really wish that you were sitting in front of me so you could see me demonstrate this. I'm going to go through and do the math. And at the end, kind of when we're finished with this problem, I'm going to show you, I've got the origin marked on my floor, and I'm going to demonstrate what's going on in this problem based on an origin and left-right movement, okay? So bear with me. Hopefully, if I say something or do something along the way that you don't understand, hang tight, watch the demonstration at the end, and then maybe you can go back and listen to me again, and it might all make sense once you realize what's going on in the problem. All right, so we've got a particle moving along a line. So it's going like left direction and right direction. This is its position function. We're looking at meters and seconds. Okay. Part A says, find the displacement of the particle during the first 2 seconds. Here's what it's asking. During the first 2 seconds, from time 0 to time 2, overall, how much did it move? Let's compare where it was at time 0 to where it was at time 2. So I literally just took 0 and substituted it in S, took 2, subbed it in. So at time 0, what is it? This is a particle. At time 0, the particle was at 3 units. 2 seconds later, the particle ended up being 1 unit left of the origin. So overall, the displacement was 4 meters to the left. It went from positive 3 to negative 1. So think about like a number line. It started at positive 3, and 2 seconds later, it was at negative 1. The displacement was negative 4. All right. Part B, average rate of change of position. Remember, the velocity is the rate of change of position. Average rate of change, straight up slope. I need 2 points, y2 minus y1 over x2 minus x1. So my 2 points are going to come from the first 4 seconds. T equals 0, t equals 4. At time 0, the position was 3. At time 4, the position was 3. It was right back where it started, 4 seconds later. The average rate of change is y2 minus y1 over x2 minus x1. There you go. Part C, instantaneous rate of change. What's that make you think of? Derivative. So for part C, instantaneous. Instantaneous rate of change means let's do a derivative on position. There's my derivative of position. And when t is 4, I sub in 4 for t. Notice how I'm labeling, right? No random math. I sub in 4, I get 4. Sub in 4, 8 minus 4 is 4. Okay, that one's done. Part D, find the acceleration. Oh, easy. Acceleration is the derivative of velocity, second derivative of position. I just got 2. The acceleration is a constant 2 all the time. It's like a force being applied in the positive direction, a force of 2 all the time. And E, okay. E asks, describe the motion of the particle When does the particle change directions? Okay, so here's what this is asking. Describe the motion. Where did it start? Like position. When was it moving to the left? Okay, think about a number line. If you have a number line, to the left means negative velocity. When was it moving to the right? Positive velocity. When was it stopped? Zero velocity. Where did it start? When it began, was it going right or left? When did it stop? Where did it stop? And then did it change direction? So, I believe that the particle was stopped whenever the velocity is zero. I don't think something can have a velocity of 1 and you consider it stopped. The velocity had to be 0 for it to be stopped. So when did this happen? Well, let's find out. So sub in 0 for velocity. Okay. The only time it was stopped was at 2 seconds. You're like, wait. What about at 0? Here's what you're going to find during these little calculus pseudo experiments. So this little experiment where a particle is moving left and right. The particle was already doing its own thing. We happened to come in and say, you know what? I'm going to watch it. I'm going to watch the particle starting now. So the particle was already doing its own thing. It was already somewhere. It was already somewhere when our experiment started. So it wasn't like the particle was just hanging out at the origin saying, tell me when to go, tell me when to go, tell me when to go. It was already doing its own thing. We decided, hey, let's do an experiment on it. Okay. So anyway, it was stopped when t equals 2. Now, that's the only time it was stopped. So if it changed direction, if you changed from, you were going left and then you go right, you have to stop in order to change direction. So at t equals 2, here's what I'm going to introduce to you today. This is called a sign chart. I would like to look at the direction of the particle, and to look at direction, left versus right, we're going to use velocity, okay? So I'm getting ready to make a number line. And in the middle of my number line, I'm going to put where my velocity was 0. So I'm going to call that 2. Notice out here I've labeled my number line with velocity, okay? So how about, this is 2 seconds. I wonder, what direction was it going at 2 seconds? It wasn't. It was stopped. It was stopped at 2 seconds. Okay. Before it stopped, I wonder what direction it was going in. So like at 1 second, maybe. I wonder which direction it was going in at 1 second. So to figure that out, watch what I'm going to do. Let's look at the velocity when time is 1. Where is velocity? Okay. Velocity is this 2t minus 4. So just so we can see my number line, I'm going to use this little expression right here. This little expression represents velocity. When I sub in 1, I get an answer for velocity that's negative. I think that from time 0 to time 2, the particle was traveling to the left because my velocity is negative. How about later on? How about at, I don't know, 10 seconds? So how about at a time after 2? You might choose 3, I might choose 10, somebody else might choose 100. Let's figure out what V of 10 is. V of 10 is, I don't know, but definitely positive. So from 0 seconds to 2 seconds, it was moving left. It was stopped at 2. Beyond 2 seconds, it was moving right. Did it ever stop and change direction again? No, never. How do I know that? Because we already found the only possibility where velocity was 0. This is the only time this particle was stopped. It never stopped from 0 to 2, and from 2 on, it's never going to stop. I know that because I set my velocity equal to 0, and I only found one answer. Okay, so here is my answer to all of this, part E. Ready? I believe the particle began at a position of 3. And just in case you don't know how I know that, I found it right here. Particle began times 0 at a position of 3. Okay, there we go. I think it was moving left from time 0 to time 2. Notice I did not include negative infinity in my time. No negative values for time. And why did I put a bracket around 0? Because 0 is the moment the experiment began. And remember, the particle was already doing its own thing. Technically, velocity is negative for all values of t from negative infinity to 2. But when I go to answer the question, I can't say it was moving to the left from negative infinity to 2 because time can't be negative. So, from 0 and including 0 to 2, not including 0. You know why? It wasn't moving left at 2. It was stopped at 2. Where was it then? On the number line. Where was it? I found this somewhere. Yeah, right here. It was at position -1. So it was stopped when time was 2. This is where it was located when it was stopped. And then it moved right from 2 to infinity. Never stopped moving right. Don't include the 2 because we know it was not moving right at 2. It was actually stopped at 2. Okay, now I'm going to do my best This is the reason right here that I have a sign in my classroom taped to the floor that says origin. So you still have your notes in front of you, and I'm going to pretend that I'm the particle, okay? I had to take my shoes off because I'm wearing sandals, and I'm going to end up tripping if I leave my shoes on. So if I'm a particle, I'm currently standing at the origin. Now, I hope this video doesn't flip around backwards, because the way that I think you should be viewing it, if I'm a particle that has a positive velocity, I should be moving to your right, which means I should be going this way. And if I have a negative velocity, I should be moving left, so I should be moving this way. Okay? So in this experiment, we had this particle that was just moving around. Actually, no, it wasn't. It was just, let's see, what was it doing? From negative infinity to 2. Okay, so from negative infinity to 2, it was moving toward the left. I am moving toward the left, but you can't see me. All of a sudden, somebody says, hey, let's do an experiment on this particle. So at time 0, at time 0, the particle's position was at 3. I've marked off 1, 2, 3. So the position of the particle was at 3. 2 seconds later, its position was at -1. 1,001, -1. It stopped. And then it started going right. That's what happened. Now, if I hadn't done all that work, so if all I knew was that at time 0 it was here, and at time 2 it was here, if that's all I knew, if I didn't know anything else, well, what could have been going on was it could have been moving a little bit this way, and then moving a little bit this way, and then at 2 seconds it ended up over here. That didn't happen, because the only time its velocity was 0 was at 2 seconds, and its position was -1. Hope that makes sense. And I hope that you're able to do these all on your own.